Yeah, so recording.
Got it.
Okay.
Yeah, so I guess now you have to start admitting people because you are the host.
Okay. Really quick before I let them in, Sadiq, are you, I guess maybe I should pause the recording. Hi everyone, welcome to the UC-ANR water webinar. This is our first one of 2023. We're delighted to have Erica. Erica, could you say your last name for me, actually?
Sure. I go by Woodburn or Sorella Woodburn. So
Okay.
either's fine.
Okay. So yeah, we have Dr. Erica Sorella Woodburn. She's a research scientist in the Earth and Environmental Sciences area at Lawrence Berkeley National Lab. She has a PhD in hydrology from Colorado School of Mines. And so we're really excited to hear about the recent advances in modeling of atmospheric rivers and everything else you've got in store for us today. So thank you so much for coming to give this webinar. We're going to go till 1 p.m. And yeah, feel free to sort of take the first like 40-45 minutes, however long you would like for your talk, and then we'll do Q&A at the end. If folks, since we're recording this and we're planning to host this on our YouTube channel after the fact, if folks who don't want to be recorded want to just type their question in the chat, I'm happy to read it out at the end. And UC folks can unmute and ask directly. But yeah, we'll hold the questions until the end. So yeah, the floor is yours, Erica. Thank you.
Okay. Yeah. Well, thank you both to Safiq and Ellen for the invitation, and I'm really excited to be here virtually speaking with you today about some recent work out of my group, really on the idea of a changing hydroclimate, specifically on California and water resources in the West. And so this is a just snapshot of a few recent studies and sort of direction that we've been working towards. And by no means is this my work in entirety. So definitely a long list of co-authors listed here, and a lot of contributions from my colleagues. So I'd like to acknowledge them before I begin. Okay, so if you live in California, then this really needs no introduction, and that's that historically California is characterized by a very variable hydroclimate. And you can see that by the Palmer Drought Severity Index plotted here over the last several decades, really alternating between periods of dry and wet. But what is sort of unprecedented is that there are these rapid changes in short order and in short succession. And this concept of whiplash is becoming more and more evident in recent years. And this is due to, as we know, anthropogenic climate change. So a few examples here. In 2014, let's see if you can see my mouse, yes. In 2014, we had a record prolonged drought that was only sort of ended through a really large precipitation year in 2017 and several atmospheric rivers which came through. But the effects of the drought are and were realized through several large-scale wildfires, 2020 being the single largest burn area year in historical record. And so if you didn't experience these impacts directly through water shortages or through wildfire in your area, you most certainly felt those effects through decreases in air quality, for example. And then, you know, the last several years have had other abnormalities in terms of what we see in the record as well. Not only between years, so intra-annual variability, but within a single year, variability. I think I said those backwards. So intra-variability within a year. 2020 was a good example of that, where we had big winter precipitation in just December, and then January, February were nearly dry. And this is sort of a almost laughable picture of April 1st snowpack measurement. So that's when peak SWE, snow water equivalent, is thought to be its is historically at its around its peak. And you can see there's hardly any snow there to even measure. And then again, you know, this is really recent in everyone's minds. 2023 so far has also been pretty extreme in terms of, again, atmospheric river occurrence and severity. And we're, you know, drying out, so to speak, across the state and feeling the sort of devastation and impacts of many of these storms still today. So that's all to say that past trends cannot be used as a predictor of future hydroclimate. And all these things together have potentially compounding impacts on the way we live and the way we manage water resources in the West in California. So today I'm going to really focus on two sort of subsets of this in terms of why California is especially susceptible to impacts in changing climate. The first is that the occurrence of our how we get most of our precipitation is really in just a handful of storms per year via atmospheric rivers. So I'll talk about that first and sort of focus on some modeling techniques that we've been developing to try to quantify these shifts in storm behavior. And the second is that, so why is California susceptible? The second reason that I'll talk about today is that a large fraction of Sierra Nevada precipitation occurs at or near freezing levels. And what that means is small changes in temperature have potentially outsized impacts on rain snow partitioning. And so I'll discuss that a bit as well. And then finally, you know, to provide some insight and a path forward and potential climate adaptation strategies as well. So first, let's focus on the fact that precipitation comes in just a handful of storms per year. So I already alluded to this. Most of our precipitation in California is derived from so-called atmospheric rivers or ARs. And these are tropically derived, very thin shaped storms that travel really large distances across the Pacific before landfalling onto the western coast. And these changes in frequency and severity of ARs has been studied recently, for example, by a colleague at mine at LBNL, and shown that basically some of these shifts in AR frequency and severity are thought to increase in the future. For example, between 1985 and 2015, you see a large uptick in both frequency and severity by end of century. And the category of ARs is between 1 and 5, 1 being mostly beneficial in terms of water resources, and category 5 being mostly hazardous. And you can see on the right here that not only the number of storms is thought to increase, but also the severity. And what does this mean in terms of degrees of warming and where these ARs are occurring? This is sort of another study out of Berkeley lab, which quantifies this a bit more, but I really just want to focus on the fact that in terms of potential flood damages, a few degrees of warming can again have really outsized impacts in terms of damages, in this case up to 3 times in financial impacts just by flooding alone. So today what I'm going to focus on is not just the flooding piece, but really what it means for more of these storms to be at the central of our water resources, and what it means for more of these types of storms to be, again, more severe and more frequent in terms of our water energy balance. So as I'm showing here, over the last decade or so, the hydrologic community has really moved towards this consideration of the Earth's so-called critical zone. And that's the region extending from the bedrock to the top of the vegetation canopy. And thinking about how atmospheric rivers play into, for example, impacts to groundwater storage, ecology, surface water, subsurface water feedbacks, and fluxes of water back to the atmosphere is really an open science question that we are asking in terms of how do we better quantify what these impacts are going to be on watershed hydrology. So in my group, we are using integrated hydrologic models with the use of high performance computing to ask some of these critical zone questions. And we specifically use a code called parcels CLM, which is just an example of many different integrated hydrologic models available that basically cover this continuum across the critical zone, from rock moisture to near surface hydrology, including the land and vegetation dynamics. And because of high performance computing, we're able to capture many of these sharp topographic changes in wetting fronts and in topography and in terms of wetting fronts. And we can sort of ask these questions at decision relevant scales. But importantly, we can also get the connection of many of these processes together as they're co-evolving through time. So things like surface water runoff and groundwater flow, while we have this changing atmospheric forcing. And so I'll talk today about how we've been coupling some of these integrated surface water, groundwater codes with tracking in the atmosphere to identify when these atmospheric rivers are occurring and basically tag that specific type of precipitation and tag it as it's moving into the system and follow the full life cycle of that water to differentiate if AR precipitation behaves differently than non-AR water. And so, yeah, we have a paper in review, or hopefully this will be readily available for everyone to read soon. But the idea is that we have particles that enter the surface through an EcoSlim particle tracking capability. We tag those particles as either rain or snow, and then we can basically follow to see if this water is lost through evapotranspiration, if it is lost through discharge, or if it stays in the system as groundwater. So that gives us not only the rain snow partitioning, we get the flow pathways and the residence time. And again, we're doing this at decision relevant scales. So today I'm going to show some recent work in the Cosumnes watershed, a sort of a case study where we've been working the past several years to ask some of these questions. And the Sierra, the Cosumnes is sort of representative in many ways of many Sierra Nevada Central Valley watersheds and watersheds across the state that are important for water resources, because it spans this interface of the mountains and the valley. Because we know much of the precipitation occurs in the mountains, runs off as snow melts, and then infiltrates into the Central Valley, which is, of course, an important reserve, especially during periods of drought. So it's sort of representative of many watersheds in that way. But it's sort of unique in that it's one of the last flowing rivers out of the Western Sierra Nevada without a major dam. And so this gives us an opportunity to basically distinguish water management effects from those of climate change. And so this is where we've focused many of our efforts the last several years. And I don't think I pointed out, here's the Cosumnes here. So Central Valley is in the middle, the mountains are here on the right. You can see the bottom of Lake Tahoe here, and the San Francisco Bay Area is here. So roughly southeast of Sacramento. And so we've been developing this model using Parflow CLM over the last several years. Faji Maina was a previous postdoc of mine and developed and did several model verification activities of this code. So I won't belabor this, but just to say that you can find more information about how we developed the model and how we verified it, for example, against stream flow, gauge discharge, water table depths, some in situ observations, but also with remote sensing for things such as snow water equivalent, soil moisture, and ET. Okay, so now going back to ARs and how thinking about recent years in the state's precipitation history can be used as sort of partial analogs of a changing climate. In the first slide of the presentation, I pointed to 2017 being a really wet year, especially in Northern California. And in the subsurface watershed, you can see on the left here that this was actually one of the wettest years in history. There's an over, I think 108 or 110 year stream flow gauge in the watershed, which actually shows the largest amount of discharge for 2017. So we thought this was a good place to start in showing the implementation of the atmospheric river tracking capability with the subsurface tracking capability combined. And so, yeah, this is basically some of the first results of that capability for this single water year. And what you can see is over the course of a water year, beginning on October 1 of 2016, we can identify 10 specific AR events. We do rain snow partitioning for each of these events, and then we can look at sort of the cumulative behavior of rain and snow, AR versus non-AR water in the watershed. And you know, it's pretty typical of many AR events in that they're, again, tropically derived. So there's a in this case, a majority of the precipitation from ARs is coming in from rain versus snow. And on year-end total, you can see that AR precipitation is slightly the majority in this case, on the order of 52%. So the question again is, where does this AR water end up? And is it different than non-AR water? And again, the advantage of this new particle tracking technique is that we can explicitly follow the source of the water, if it's rain or snow, and see if it ends up as groundwater storage or exits the watershed via discharge or ET. So this is a bar plot for each of those 10 AR events that I just identified on the last slide, but now we're distinguishing the phase and water year end compartment. And so by compartment, I mean is that water ending up as ET, discharge, or groundwater storage. So in this case, any water that's exiting is shown on the top of the bar graph. So red is ET, blue is discharge, and any water staying in the system is on the bottom for groundwater and shown in those gray colors. So then you can also not just look at the 10 events, but also the annual sort of average of these different storms. And you see a few different key points. So first, despite the ARs having more incoming precipitation than non-AR events, less of this AR precipitation ends up as groundwater storage. And that kind of makes sense. They're bigger storms, they're more intense, so you get more runoff. Second thing that we notice is that if we filter the contribution of discharge from rain on snow events, we see that over half of this discharge is actually from rain on snow events. So it's quite significant, and it's sort of a specific marker of these types of storms that could potentially be pretty outsized in terms of its impacts. So another way to look at this is now to look at the same bar graphs, but now all normalized by precipitation in order to see just the behavioral trends. And again, we can compare the year-end AR versus non-AR water. And the biggest difference here, which I'm highlighting with these two arrows, is basically that behaviorally or fractionally, ARs result in far less, over 3 times less, groundwater storage from snow than non-ARs. And so this, again, connection between how these storms come in, how they have different intensity, propensity for rain versus snow partitioning becomes really important. And this connection between ARs and snow is potentially, you know, just looking at a single water year 2017, where we have more of these storms, can point to things that we can study for the future. So, you know, this is sort of a first example of this. It's a single water year, but we hope to extend this and catalog more years and more different storms to look at this in the future. But it sort of leads me to my sort of second topic of today's presentation, which is that really around this idea of the importance of the snow line in the Sierra Nevada and how incoming precipitation becomes partitioned when we have this real sensitivity to temperature. and the importance of the connection between ARs and snow is sort of an example of that. Okay, so again, why is California especially susceptible to changes in hydroclimate? Well, a large fraction of the Sierra Nevada precipitation actually does occur at or near freezing. And so this is a really nice way to demonstrate that from Roger Bale's group, showing that sort of contrary to some of the interior ranges like the Rocky Mountains, the Sierra Nevada and the Cascades really have this sensitivity in terms of temperature, and that you get a larger fraction of precipitation that falls as rain. And so what that means is that a really small shift in temperature can have a big impact, an outsized impact on your precipitation phase. And as we move into a warmer climate, you can have more rain and less snow. And so if you study water in the West, this is no surprise to you, but just to point out, why snowpack changes are really important. I want to talk about kind of two central pieces around the assumption of a reliable snowpack and why that can break down with the changing hydroclimate. So first kind of consideration here is just storage of water. And if you think about historical snow water equivalent and the amount of water stored in snow versus the amount of water stored in reservoirs. So our largest reservoirs in the state shown here in this dark blue, the smaller reservoirs shown in the light blue, they're roughly equivalent. So snow naturally accounts for an additional 72% of storage relative to some of our man-made infrastructure. Okay, so snow also melts every year. So there's a seasonal storage piece of this as well. And historically, you can think about water and supply sort of having overlapping but not coinciding signals where, water is slowly released into the winter and spring and demand increases in the spring and summer and into the fall months. But into a future where we have a shift in sort of the availability of snow and potentially earlier melt of snow, this line, the supply line is basically going to shift earlier. Assuming your demand is the same, then there's the potential for shortages in a changing climate. So it's not just the storage, but also the timing of snow and providing this resource for us in terms of when and how we get water. So last, I guess, a year and a half ago, a group of us came together to really ask the question of, well, we know that these warming trends are occurring, but what is the timeline of continued snow loss? This is already something that we see in the historical record, but when is snow loss and some of these bigger changes going to be a persistent thing that we see in our climate? And we have this study in Nature Reviews, which basically seeks to answer that question. And so we went to the literature and did a pretty comprehensive projection synthesis, Western US wide, to better quantify when some of these expected changes in snow could occur. And I won't go into all the details, but the paper is here. And basically, we looked at different basins and we put together a proposed definition of what we call low to no snow, based basically on percentiles of peak SWE. And again, look to the literature to try to synthesize these. And across several different studies, you can see that Western US wide, this change in snow availability will likely have an impact within the next 35 to 60 years. But in California, that could be sooner. That could be actually within the next 20, 25, or 30 years. And this is just a single example of one model projection with the high emission scenario that kind of shows that transition from just single year or extreme snowpack loss years to where this is more persistent by end of century. And quantitatively, if you're interested, historically we see these low snow years happening on the order of 10% of years, and by end of century, that's quite substantial, almost the majority, 90% of years. And again, it's not just when snow snow changes might occur, or when these changes in atmospheric rivers might occur, but what does that mean in terms of where the water goes? What does it mean in terms of our water resources and stream flow or groundwater? And to answer that question, you really have to consider a lot of different co-evolving hydrologic and atmospheric processes. So part of this nature review paper was synthesizing some of these changes and trying to put forward a blueprint of how our scientific community can come together to better constrain how and when some of these impacts from a changing hydroclimate can, when that's going to occur and in what ways. So just as a few examples, if you're thinking about changes in snowpack and what we call a low to no snow future, you might have changes in your vegetation. You might have more prevalence of high elevation wildfires that impacts your solar radiation budget. And because of warmer temperatures, you're going to have more evapotranspiration, and that all impacts eventually how much water is getting into your streams and into your groundwater aquifers. But because many of these processes, again, are competing, it's pretty difficult for us to make some of these inferences. And so another way to think about this is by just schematically sketching out some of these top-down processes in snow. So you have let's see, sorry, that's very small for me to read. You have let's say an average snow year. You have shifts in your rain snow partitioning that has an impact on your soil moisture, your evapotranspiration in your groundwater, and your discharge. You can play these thought experiments. Well, what if you have earlier snow melt? What does that do to your soil moisture? What does that do to your discharge? And as you see, if you move forward in these scenarios and you move further down this top snow to groundwater and discharge continuum, more of these kind of question marks come up, and it's more difficult to make these inferences. And that's again where critical zone processes that are co-evolving, often non-linear, are really difficult. And that's where we point to the models as a tool, to a key tool to better sort of disentangle these things. So briefly, I'll just go through another study, example study, where we're doing this again in the Cosumnes watershed as some of our first looks at how to couple some higher fidelity atmospheric simulations with these integrated groundwater surface water models to ask some of these questions. And specifically, we're hoping to move away from quote unquote pseudo climate warming or delta approaches, where you say, well, we know there might be a 2 or 3 degree warming in the atmosphere, and that's going to result in this sort of hydrology. No, we really hope to better simulate some of these atmospheric processes themselves with Earth system models. And because of high performance computing, we're able to do this with variable meshes and variable resolutions to get down to the resolution of something closer to that, or discretize the watersheds such as the Cosumnes in a way that we can provide high fidelity forcing. And so this is one example of such a study that we published last year in PES. And so specifically, we use RCP 8.5 emission scenario with the VRCSM or system model. And we take an ensemble of 30-year historical and 30-year future simulations. And we're just asking the question of how do the extreme years start to vary? So we look at changes in precipitation and temperature, which are plotted as the 2 axes here. In the historical, we identify the driest, the median, and the wettest year, and then we do the same thing for the end of century. And this is again important because we're jointly considering those thermodynamic and dynamical processes in the atmosphere that connect from global to regional scales. And so let's see, I think I'll just dive into some of the results. So I showed earlier just a schematic of kind of a hydrologist's guess of what some of these shifts, co-evolving shifts in in the water energy balance might be given lower snowpack, giving bigger and more intense storms. And so now we're just relying on the model to quantify some of these things for us. So now what I'm doing here is just showing again, those 3 years, a median, a dry, and a wet year for historical and end of century, again, from those 30-year ensembles. And you can see a few things. So in the future, the simulations show that the onset and the end of precipitation is earlier in all cases, really except the end of century dry year. That's because it lasts longer. And importantly, thinking about rain and snow partitioning, you see that rainfall has a dramatic increase and snowfall has a really dramatic decrease in all cases. And you can see that's really especially true, for example, at the end of century wet years, you have almost all of your precipitation falling as rain instead of snow. Sorry, that's what I just said. Yes, I'm sorry. The snowfall is mostly as rainfall here. Sorry, the precipitation is almost all rainfall instead of snowfall here. And then what I'm showing here is basically the change in SWE, snow water equivalent. And so because you have such little snowfall, you basically have almost nothing in terms of snowpack. And again, this is a combination of warmer temperatures, but also other physics, things like rain on snow events. And I just wanted to note here that within that ensemble of 30-year simulations, the 3 identified years in terms of precipitation are actually on the order of 4 degrees warmer, but the cloud of simulations could show simulations being or average year, some of these years could be on average 1.5 degrees warmer. So there's even scenarios in the future that could have even less snow than what we simulate here. Okay, moving down that continuum of atmosphere through bedrock, if you look at soil moisture, end of century soil moisture is projected to be wetter and dry more quickly, sort of consistent with precipitation. ET is substantially higher, mostly due to some of these temperature-driven potential evapotranspiration shifts. And in some scenarios, you get over 2 or 3 times annual ET by the end of the year. And finally, sort of regardless of the end of century ET, changes in these fluxes, we show that the groundwater and surface water storage is largely greater in end of century, which was sort of maybe not to be expected, because a lot of the literature does point to wet's getting wetter, dry is getting drier. In this case, many of our simulations just showed this propensity for wetter. So this sort of summarizes many of these comparisons where, it's a bit dense to look through. Maybe perhaps I'd refer people to the paper, but basically we're just scaling each of these infographics to give a summary of what some of these extreme years could look like into the future. But I guess some of the big takeaways are, again, these big shifts in rainfall, really large decreases in snow and small snowpacks, really large impacts in evapotranspiration, and then subsequent impacts on the groundwater and surface water hydrology. But I guess some caveats here as well. We also show that spatial temporal trends matter. And so many of those numbers are just looking at all those numbers I just showed, we're all looking at the watershed average. But if you dig down into some of the spatial patterns, you can see some sort of interesting and distinct changes. And so one of the things that I found really interesting was that surface water storage, sort of on average, we saw had this sharp recession in terms of how fast the base flow curve declined. But if you look at the spatial trends, you see really that there's more channeling of water into these streams. So you actually have an increase in the amount of water that's in the main stems of the rivers and a drying of the lower order, smaller streams. So you get basically more ephemerality in the future with warmer conditions and less snow. So yeah, I'm happy to answer more questions. That was a lot in terms of some of the details there, but I just wanted to take a few minutes to end with thinking about strategies in terms of climate adaptation and sort of recommendations, so that this is you know, not so doom and gloom, because there are a lot of things I think that we can suggest and put forward as scientists, but also not just focusing on many of the uncertainties, because I think there's definitely some concrete things in terms of changing hydroclimate that are available already. And so one quick note is to say that some of these shifts, and specifically a change in snow and a low to no snow future, is not necessarily set in stone, because there is large potential to limit the amount of warming, especially in the Sierra Nevada, with commitments, for example, to carbon neutrality and transportation and building, investments in renewables and short and long-term energy are really a key piece of this. And so colleagues of mine have put forward sort of blueprints for this, and I think that's really powerful to point to. And in terms of sort of different areas where water resource management can be, it is already mature in many ways, but can be also advanced, is something we actually discuss in this Nature Review paper. And we kind of categorize this into 4 distinct ways in which changes in water supply and management can be progressed. So thinking about just demand. So how do we irrigate agriculture? Can we improve efficiency, crop switching in our urban areas? Can we you know, do better leak detection? Can we have better water capture and localized storage? Thinking about new sources of water, new meaning sort of widening the portfolio of ways that we utilize the water that we have. So forest management is a nice one, I think, to point to, because you could have sort of mutual utility in terms of wildfire prevention and also reduction of evapotranspiration, potentially saving some of this water. Thinking about fully engineered systems such as desalination would sort of fall into that category as well. Adapting existing infrastructure with new management. So this is things like forecast informed reservoir operations or managed aquifer recharge, which given you know, the intensity of AR events and essential loss of much of this water as we follow really historically informed rule curves of how we manage aquifers, you know, and watching much of this river water run off into rivers and eventually into oceans, I think is difficult when we do have these ongoing drought issues. So managing this hydroclimate in face of some of these whiplash, I think, is another really important area. And then, of course, I think, you know, it's never off the table, I think, in terms of new site development or retrofitting of existing infrastructure. So I think it's a portfolio approach. I don't think there's a single silver bullet for any of this. And hopefully some of the science that we're learning in terms of the integrated watershed hydrology can help to inform how the system will respond in some ways and better quantify sort of the magnitude of how some of these different storms or different you know, a way we get our precipitation in the future, for example, with low to no snow, what that means for ecosystems and what it means for groundwater reserve, what it means for reservoir storage. So I hope to yeah, I hope to answer any questions that folks had, or just to have a nice conversation following this. And just to conclude that I think there's a lot of promise again in some of these tools where we're coupling the atmosphere and hydrologic models because of these co-evolving and nonlinear feedbacks, and just that there really is no silver bullet. So I think it's a important time for stakeholders and scientists to come together to sort of mitigate some of these potential climate disasters. So I'll leave my email here and happy to answer questions or, as I said, have a discussion. So thanks again.
Thank you so much, Erica. Yes, folks should please feel free to either type your questions in the chat or go ahead and unmute and ask. I'll go ahead and kick it off with a question that I have. So I thought it was really interesting looking at you know, the graph you showed from, I think it was from the Nature Reviews paper, showing like by the end of the century the persistence of the low to no snowpack. And I was just curious, in when you're sort of doing these simulations and projections out into the future, like how do you think about things like reservoir management? Because I would think, well, I guess if it's just the snowpack, maybe it doesn't matter. But in certain things related to like the water supply, like reservoir operations, like factor into that too. Like there's this human component, and like how do you approach that in thinking about projections and simulations out into the future?
Yeah, no, I mean, yeah, exactly. I think that's why it's complicated. You know, much of this Nature Review study was just focused on the snow and the persistence and prevalence of snowpack. But as a hydrologist, I'm really interested in what happens to the water after it melts. And so, yeah, and you can look to, again, some analogs of recent years when you have these big storms and you have, for example, really dry soils. You know, the impacts of these storms are not felt in terms of flooding in other ways as, say, what we experienced a few weeks ago when we had really wet soils. So there's yeah, that's all to say that there's there's not a direct link between what we see in the hydroclimate and what we see in the hydrology. And that's why, for me, the models are really important tools, because I have a hard time, you know, making these inferences about what it means for something like discharge. And then, yeah, there's other complicating factors on top of it. So you can have rain on snow events that, you know, a perfect example of that was the collapse of the Oroville Reservoir, you know, where it was like, it was not expected at all in terms of how they were operating the reservoir. Right. And they had this big melt event. Or another one would be like snowpack melts from, you know, shifts in albedo, given we have many more wildfires, and so, you know, we have faster melting snow. So I think, yeah, it's just a hard relationship there.
Yeah. Of all these different components of the hydrology, like we have these, like, yeah, I don't know, interconnected features of the landscape affecting the hydrology. Like, are there certain components of it that you would say there's a lot more uncertainty around than others?
Yeah, I think for one big thing I think is lacking is connection of evolving vegetation. So especially when you're thinking out like decades. So you know, and there are pretty sophisticated dynamic vegetation models that do some of these long-term, you know, evolutions. I'll say, like, you know, a shift from grass to shrub or something. But connecting those with the hydrology models and the atmospheric models, I think, is really disjointed right now. So a lot of the time it's like, well, we can make these assumptions that maybe, you know, you will have this change in your vegetation by this much. But that's, again, a co-evolving thing, you know, given especially there's dependence on deep groundwater in many forest regions, that, you know, they're not actually physically disconnected. So we often have to make these assumptions. So I think for me, it's like many of the land surface processes.
Yeah, that makes sense. I'm also curious, like what you have in the pipeline, like what are you working on in your research that's kind of like the cutting edge for you right now?
Yeah, good question. I mean, I'd love to extend the coupled atmosphere and subsurface tracking, like I said, to have like a much bigger catalog of AR events, because we've only so far done the single year. And so that's some things I like to explore, especially with different sequences of storms. I guess I'm really interested in sequencing in general, like if there's a bunch of storms that are in short order falling versus distributed more over a longer period, or if you're following a really dry year, so that gets again to the interannual variability, or if you've had multiple wet years in a row. I have, and I showed this in AGU this last December, I'm working on low to no snow sequencing in the Rockies, so not California specific, but the Rockies, as I showed, are in some ways a bit more resilient to many of these shifts because of the higher snow fraction there. And so I'm kind of interested in identifying tipping points in, like, as I'm showing on this figure here, when do you start moving from extreme to persistent conditions, and how is that connected to buffering and groundwater, and like what are the drivers of that? So we're connecting to observations in that project as well for deep groundwater age dating, to see how that plays in. But again, I think some of the vegetation pieces, when you're running models out for so long, at least hydrologic models, is sort of a key area where we need more software development.
Yeah, for sure. That makes sense. Are there any other questions from the audience? Well, I'll just say, Erica, I'm an economist. I'm a water resource economist, and a lot of my work is around like policies related to demand management of water in California, and so like it's this kind of work that's very like motivating for why we might care about demand management, and so it's really helpful for me to get a deeper sense of the hydrology and the future of it in California in particular. So yeah, I learned a lot from this. It was really helpful for me. I'm going to check out your paper, and and yeah, so I really appreciate you doing this.
Yeah, no, definitely. I'd be happy to chat, and likewise, if folks have other questions, I'm happy to follow up offline. So appreciate it. Yeah, thanks for the opportunity.
Great. Thank you everyone for coming.
Okay, take care.
Bye, Erica. Thank you.